Okay, so again, I just want to reiterate that the key idea, or at least the most basic important idea you want to take away from the design of a randomized procedure is that a clue that you might want to be randomized is if you're trying to be deterministic and the adversary is able to supply you with these worst case inputs by very, very carefully choosing them. So the adversary has to do a lot of work to give you this worst case input, but they can do it. And that suggests that if you sort of to mix things up and be randomized in some form, then the adversary no longer can construct that carefully crafted input, and that might give you some leverage to improve the behavior of the output. Okay? There are many, many other signs that a randomized report should be useful. I've taught entire classes of randomized algorithms, so we can't go into all those here. But this is probably the most basic one. And at least for some of the examples we're going to see over the next few lectures, this is going to be the thing that makes it work. The idea that in order for the deterministic to be bad, something really strange has to happen. But if since it's worst case, we have to account for it. And so by being randomized, we won't have to account for it. Okay? All right. So today we're going to talk about probably the most ubiquitous application where randomization is almost essential, as well as being something that you use all the time, hashing. And so what is a hashing? What is the problem of hashing? And so let's just think about the problem further. So basically, hashing is a solution to a problem, the problem being the dictionary problem. So what is the dictionary problem? The dictionary problem says, I have a universe of elements, so we'll typically call this U. So this is the universe. And usually the universe will be very, very big. And the example I always go to when I want to think of very, very big is something like I'm using IPv6 addresses. So the universe is of size 2 to the 64. It's a very large universe. Okay? And now I have a collection of elements from this universe. Let's call this S. So S is some subset of U. And S is of size n, right, which is much less than U. Right? So I might have a router dealing with actual IPv6 packets, right, at a particular server. There may be a few billion of them. That's still very, very small compared to the size of the universe. I want to build a data structure. So that's a dictionary I'm going to build. So I want to build a data structure. So some kind of data structure on S, such that I can answer the query right? Is the most basic question you could ever think of. Is an element in a set? Right? Set membership. What could be more basic than that? This is called the dictionary problem. And of course, the dictionary problem has many solutions. Possibly the easiest solution is to store some kind of... So, okay, before I even say that, what would I want from the solution? So what I want is that, I want a couple of things, right? I want, and this is true for any data structure problem. So you want that the space of the structure is small. And you want the query time to be small. Right? Obviously, right? We want small space and we want small query time. And the question is to what extent, and so typically when we think about small space for these kinds of problems, we might say, well, if I have n items, I have to store the n items maybe, but I don't want to store much more than that. So I'm willing to pay linear space, but I don't want to pay much more than linear. And the query time to be small, well, of course, the ideal case is a constant query time. But something, as close as I can get to that. And maybe I can get it, I don't know. Now, there are many ways to even think about this problem. Right? So probably the easiest way to think about solving this problem, and one that's actually a perfectly valid answer for many applications, is to do some kind of bitmap. Right? So we say something like, okay, so let's see, what is the first solution we can have here? So first solution is the bitmap solution. What does that mean? We create a bit vector. And this has U bits in it. I look at my set S. I could just put ones wherever the items are. When the query comes in, I just check. Easy. So what is the space needed for the structure? How much space do I need to store this? I need U bits, right? Okay, so I need U bits. And then what is the query type? Constant. 1. Just look it up. So this is great from a query point of view. It is absolutely lousy from a space point of view. And again, to think about that, think of your IPv6 bitmap. You have 2 to the 64 bits. Now think of n being like, a billion. I'm going to use up a billion of those 2 to the 64 bits, which is nothing. It's tiny. So it's a humongous waste of space. So I'd like to do better. Now, of course, I could do something different. So this is the bitmap solution. There's also what I'll call a binary search tree solution. Suppose my elements come from an ordered domain. In other words, suppose my universe has some notion of a less than operator on it. Now, that usually is not hard to do with the numbers. But if they're not numbers, you can even do something like lexicographic ordering. You can always put some ordering on the space, right? Even if it doesn't have one naturally. And then what do? I build a binary search tree. You all have probably seen binary search trees, red, black trees, what have you. These are trees that admit they're basically a tree structure that says, okay, you start at the top, you have a query, you go left or right based on whether your query is less than or more than the top element, and you keep going to find the answer. If you build the tree correctly, you will spend the depth of the tree to get an element. It's a binary tree, it has n elements in it, so the depth will be log n. And the space required is something like n, because there are n elements in the tree. So that's pretty good too. So that's actually much better. So the space now has gone down from U to S, which we'll remember, we're calling n. And the query time, which has gone up a little bit, is something like log n. Okay. So we have two solutions to the dictionary problem. One has horrible space and very good query time. One has pretty good space and query time is pretty decent by most standards, but it's not optimal because we know we can get a constant value. And of course the question really is, can you do both? Right? Can you get space that's linear and also get query time that's constant? That would be being greedy, but why not? Well, at least we can ask if it's possible. And there was a very famous paper, it was like 78 or something, that Andy Yao, a very famous researcher in the field, basically wrote a paper called Should Tables Be Sorted? And developed the idea that if you just want to solve a dictionary problem, you don't actually need to sort. You can do better. And while he didn't propose a solution we're going to propose here, he basically introduced, or at least was one of the people who introduced the idea of doing hashing. So hashing, as I said, is a solution to a problem. It's a solution to the dictionary problem. It's a solution to the dictionary problem that gets you linear space and kind of sort of constant time. And that's why we all use it. If you ever use hash tables in your, or hash structures in your code, this is why you're using it. Okay? Any questions so far? Alright, so let's think now about how we might build a structure that will allow us to do this in constant time. And let's see what the problems are. So, what we need is some kind of mapping function. Right? We need some way of saying, I have an element, a set of elements S, and they're drawn from this universe. I have to have some rule that says, okay, if I see this element, put it in some location in a table. If I see this element, put it in some other location in the table. I'm going to build some kind of table. Okay, so the basic hashing structure is going to be, you have the universe here. This is my universe, and I have some set of elements in it. What I want to do is make some function that puts them in a table. And so on. We'll call this a hash function. This table is going to be of size m. The number of elements, this is the universe, and these are the set of elements of size m. Okay, so these are the things we're doing. So suppose I have such a function that can do this, and let's just say, let's say for now this function is deterministic. In other words, it doesn't use any coin toss.
Doesn't use any what?
Doesn't use any coin tosses. It's a deterministic function. Okay. what would we like to have happen in this hash table? We want everything to go to a distinct point. Okay. What we don't want is for things to collide. Because if things collide, you have to do something. If things collide, one way to deal with collision is to make the table bigger. Another way to deal with collision is to make an extra thing. So for example, suppose I have two elements. Suppose my hash table here. This is one of my cells in my hash table. Okay? Suppose two elements, because of that way the hash function works, were mapped to the same entry in the table. Now I can't store them both. There's only one cell there. So one solution, let's just call it chaining, is to say something like, okay, I'm going to store this, and I'm going to create another entry here. Right, so this is A and this is B. I'll say put A here and put B. With the idea being that you just keep a list of all the things that all collide. Right. And if you have lots of elements ending up in a single bucket, you put them all in a chain. Which means now that when you have a query, when I want to know, okay, is the element C in the hash table, I will use the hash function to map C to a bucket, but that's not good enough anymore. I'm going to have to go down the chain and figure out if it was any one of those elements at all hashed into the same bucket. So the time it takes me for a query, right, is going to be something like, so the query time is going to be 1 plus L, where L is the length of the chain. Right? Okay. So the game now is as follows. We've now gone from our bitmap and our binary search tree to a table-based method. We're saying the class of algorithms we're going to consider are algorithms that come with a function, the hash function, that takes an element of the universe, does something to it, and outputs a pointer or a number between 1 and n. It says go into this bucket. We also said that if two things end up in the same bucket, then we just string them along. So obviously we want to make sure this happens as little as possible. Now let's consider a deterministic function, any function. Okay. So let's take any function. Okay. So suppose some function, and this is the function from u to 1 on n, which I'll write for short as this. Suppose which of course we want. What can we say about h in this case? So how many of you have heard of the Pigeonhole principle? Okay. The Pigeonhole principle is an important, let's say, zoological concept that says that if you have 10 pigeons and 9 pigeonholes, someone gets a room. This is a very important fact in computer science. I'm not joking. You may think I'm joking, but I'm actually not. So in general, the Pigeonhole principle says if you have n objects and you have n minus one places to put them in, 2 objects must show up in the same thing. Okay, what does that mean? If I have a hash function from u to m and m is less than u, there are at least 2 elements that must map to the same bucket. Okay? Alright. So now what's my adversary going to do? My adversary is going to look at my deterministic hash function. It's like, aha, you're a deterministic hash function. I know you have a pigeon somewhere hiding in there. So you go find the pigeons, 2 pigeons, and you construct an input consisting only of those pigeons. What's going to be the worst case behavior of this hash function? Everything is going to go to one bucket. And the query time is going to be n. That's not good. We could do much better with binary search trees. So in fact, no deterministic hash function is going to get you anywhere unless n was u, which was our bitmap solution, which was lousy for other reasons. So what do we do? Yes?
Give a random sized bucket.
A random?
A random sized bucket.
A random sized bucket. What does that mean?
Like when you build a hash table, you change the size of the table so that when you do the mod on the hash output, it changes how the things are.
So I choose a random, so I mean n is a random number. Is that what you're saying? Because n is the size of the table.
Still needs to be big enough.
Okay.
Yes.
But it still needs to be as big as u. It doesn't matter what the value is.
Can't be small.
It can't be, well, in this case, small means less than u.
Okay, then it can't be small.
So, but that's not going to work very well because I'm still stuck with needing u things. Yes?
Randomize there is a randomization in the hash function.
Right, so I mean yes, that's the whole point is that we want to somehow introduce randomness into the way we do the hashing. And this is the key to the whole way we think about randomized algorithms, right? That the inputs are causing us trouble. So we introduce randomness into the algorithm to prevent this from happening. And the intuition here is that the adversary has looked at your function very carefully to find pigeons. If you now randomize the function, the pigeon looks like ducks, and now you can't move them, roughly speaking. So how does this work? Okay, so the basic idea is the following. So what we're going to do is, what we'd like to say is, let's define a class, let's define a collection of hash functions. So we'll call this hash function H, collection H. And what we do is, we choose some hash function randomly, and this is what the notation means. It's an element randomly chosen, uniformly randomly chosen from H. Okay? And then use that for your hashing. Okay? And the hope is that this will somehow work better. Right? So what are the different ways in which we could, how do we evaluate, what we need from such a hash function? Before we figure out which hash function to pick, we need to know what we're trying to expect from it. What is the goal we want of this collection of hash functions? So what is it, ideally what do we want if we think about this? What do we want this hash function to be? Yeah.
Instead of picking the hash functions, you could assign a random variable to each of the elements, right?
And assign a random variable to each of the elements.
Yeah.
That's a hash function. And that's one hash function we will consider in just a second. But what is it that we want this hash function to do for us? So forget randomness again. Just think, yes.
So we want our hash function to distribute the elements in U evenly to the buckets.
Right. Right. So we want things to be nicely spread out. Okay. So let me give you a collection of hash functions that will do precise. So let's define that formally, right? So we might want to say something like the probability that h of x is equal to I, okay, for any x and any I is less than or equal to 1 over m, where again the probability now is being evaluated over what? Where the randomness is coming from? They're being used to generate the hashing function. So this is true for all x and for all I. Not for some x or for a good fraction x. For all x, so you fix your x and your I, you pick your hash function randomly, and now you say, was h of x equal to I? Then you do it again, and you do it again, and you essentially get this problem here. And yes, I'm a secret frequentist. So. So this is a property that seems like it would capture what we want. Okay? So it's kind of, it spreads things out nicely. So now we can say, okay, now that we have a criteria for what a hash function family should look like, let's define a class of hash functions. So let me give you a class of hash functions. So my hash function family is going to look like this. It's going to be called, it's going to be a collection of all a of x, where a belongs to 1 through m, and a of x, to abuse notation terribly, actually, let me just call it h of x. This will be really bad. It's a constant hash function. It sends every element to the location a. Is this a good hash function?
itself, no,
Why not?
because it sends everything to the same slot.
It's the exact opposite of what hash function should do. Okay, but now for any x and any I, what is the probability that h of x is equal to I? It's 1 by n. Because a is being chosen randomly. So for a fixed x and a fixed location, the probability that I choose I, h of ix as my hash function is 1 over n. So the probability of that statement being true is 1 over n. So by my claim that this was a good way to evaluate a hash function, this is a regular hash function. But we know it's not. So something's wrong somewhere. And before I tell you what's wrong and how to fix it, let me make sure you understand why this is a bad thing. Again, I had this vague idea that I want my hash function to spread things out evenly. And that's a very good intuition, right? I want hash function to be spread out. But now the problem is that my hash family, which will in fact guarantee the property that everything is spread out, is doing it not by spreading out individual elements, but by choosing a random location that everyone goes to. So on average, it works. But for any particular hash function, it's horrible. And you're always actually going to deal with a particular hash function. You're not going to deal with an average hash function. So this is no good. It's not optimizing the right thing. Because you still have a lot of collisions. So it's almost like you want something a little different. In some sense, you don't care where the item maps to. What you really care about is how many other people map there to. That's what you're worried about. So if I change this question around a bit, and I now say, well, maybe I don't care about, where it maps to, but I care about who else maps there, I can ask the question slightly differently. I can say that I want the probability, right, that h of x, let me see if I get this definition correctly here. Yeah. Is equal to h of y. Now we're talking about actual collisions, right? What is the probability that two different elements map to the same location? So condition that x is not equal to y. Should be, what do you think would be reasonable for this? Sorry?
U divided by n.
Sorry?
U divided by n.
U divided by n, but that's a big number. That's a problem. That's a number that's much more than 1.
Oh, I know.
So I think you made 1 over n.
Oh.
So 1 over n, I mean roughly speaking, right? So you want to this. And this is what is called a, if you can get this, this is called a universal hash function. And again, remember, the probability is evaluated over the choice of hash function in my family. So my game here is to come up with a family so that if I choose a hash function randomly from that family, this property will be satisfied. And it's sort of useful to analyze. Suppose I actually had such a hash function. I don't know how to come up with one yet, but let's say I had one. We can now start saying things like, what is the expected load? Right. So if you look at any particular bucket, right, right. So if you look at, sorry. So let's say we have a hash function that can do this for us, okay? And let's try to figure out what the total collision size is, right? So how do we, so let's look at the bucket that x maps to. Okay, so this is h of x. This is the bucket ID h of x. We'd like to figure out the load on this bucket. How many other things map to this bucket? Okay. So let's say that we define a variable just as before. We'll say that this variable cxy is equal to 1 if h of x is equal to h of y is equal to 0 otherwise. Right? Just like we did last time. Define a random indicator variable to capture what we want to capture. So now we can write down the load on x. So let's say the load is, we'll just call it L of x, the load on the hash bucket that x goes to, can be written as sigma over all y, cxy, right? Because it's a 1 if they collide, it's a 0 if they don't. So that over all elements in my domain, in my set, right? For each of them I check, okay, did it collide? Okay, put a 1. Did it not collide? Put a 0. So I add them all. And now I want to find the expected value of this thing. So I can say that the expected value of E of Lx, just like before, by linearity of expectation, is merely the summation of the expected value of Cxy. Right? Okay, but what is the, so, and also we know that since Cxy is a 0, 1 random variable, the expected value of Cxy is merely the probability that it's equal to 1. So what's the probability that Cxy is equal to 1? What is the probability that x and y collide at a particular hash table?
1 over n.
1 over n, right? So in particular, we can write this as Cxy, so probability Cxy equal to 1 is equal to 1 if x equal to 1, obviously. And it's equal to 1 over m if not. That's by definition of the universal hash function. That's a property of a hash function. We said there's going to be 1 over m. Right? Okay, so now we add this up. What do we get? We get that the expected value of L of x is going to be roughly n. Because there are n items in my summation here, and each of them has a probability of 1 over n. It's actually, n minus 1 over n plus 1. Okay? And we'll call this number, which is a kind of important number, so I'll define it as alpha. So, yes.
This value of n here, like it could be n minus 1, is it?
N is the number of elements in my set. Remember, I want to hash up.
So the total size is my n.
N. N.
Okay, S.
N for not N.
I was confused. Our set is having size of m total, right?
N. The hash table has size M.
Oh.
Sorry, this is unfortunately these two letters sound so much alike that it's getting confusing. But it's a standard notation. I don't want to mess with that. So, is that a good number? I mean, that's important, right? I mean, I claim that, oh, I have this nice criterion. I claim that if I have this nice criterion, I get this analysis for the load. Is that load over V1? Yes? You're saying yes? Why do you say yes? Why do you think that's the right load?
Evenly distributed.
It's kind of evenly distributed, right? If I have n elements and n buckets, I can't hope to get better than n over m for the entire thing. So that's kind of good. It's saying that on average, everything is evenly distributed. That make sense? Yes.
It means my m elements are evenly distributed. The set
N elements are evenly distributed.
n elements.
So there are n elements, there are n buckets. So think of m as 2,
Okay.
if you want, right? So it's saying there are going to be n over 2 elements in every bucket. That seems fair. If you have n elements in 2 buckets, what else can you expect to happen?
Yeah, but if the set I'm choosing all has the element on first bucket, then again it's
No, there's no first bucket here. This is true. This is the expected value.
expected value.
For any input, the expectation is over the choice of the random function. That's the thing. The input comes first and I pick randomly.
And then you pick.
So it kind of randomly scans it. Right? That's the magic of this thing. So we have a property that seems reasonable. It seems to give a reasonable output, unlike the previous property that was not giving us a reasonable answer. It was allowing the load to get very large. This is keeping the load more or less balanced. But how do we, I haven't yet told you how to come up with this. I've just said that this is a property we want our hash family to satisfy. So let's come up with a hash function. Right? So what is there is a very, well, I won't say easy, but there is a very natural hash function you can pick here. And this was mentioned earlier. You just assign x to a random number. So let's say the hash family. So let's say I have the hash function h of x equal to a random in it shouldn't be too hard for you to convince yourself, even without doing the calculations, that this function will satisfy that property. Because everything is completely random. The probability of two things colliding is going to be very small. And you should be able to work this out. Yes?
Okay, because I'm sure this is an embarrassing question, but how do we know we're going to, if we're generating these randomly, how are we going to recover this when we need to look up our element?
That is in fact not an embarrassing question. It is the question that strikes a deep dagger to the heart of this hash function. You just kill this hash function.
Yay!
That's a very good question. I'm going to get to that in just a second.
Okay.
Yeah, that's the reason why this hash function is going to fail us in this group.
Okay, here.
You killed the suspense.
Sorry?
She killed the suspense.
She killed the suspense. You've all been doing this. Every time I think, okay, I will hide the answer, then someone comes with the answer, like, fine, you're all too smart for me, it's okay. But that's good. We shouldn't have too much suspense in the class, it gets tense. So this, again, my suspense is good. Anyway, it has the right property, but it won't work for exactly the reason it carries. Namely, the following. There are two ways to think about this. So first of all, how do I define the family of hash functions? I said the h of x is a random location, but I said I have to define some family. What does my family look like? It's a family of hash functions. You can think of this family of all random permutations. Right? The hash family is a set of all random permutations of 1 through n. Or all random mappings from 1 through n. Okay? So there are two ways to think about why this is a problem. So the first way that you mentioned is that, so h of x is a random location, so I put in the random location. Now sometime later on, I have a query. Is x in this set? What do I do?
Panic.
After I finish panicking, what do I do next? How do I figure out if now x was in my dictionary or not? So my answer is, well, I just run the hash function. How do I run the hash function? Do I know the random value? Well, maybe I can store it somewhere. So now I have a new dictionary problem. What is the random value that corresponds to my x? So I can go look at the other hash table and find out where x is. So even though this hash function does what we want, we don't know how to show the answer. So that's one way of thinking about why this breaks. Let's think about it a different way. Okay? I have to describe this hash function to you. If I have a hash family, how many bits will it take to describe an element of a family? Well, I have a set of objects, and if there are, so let's say I have a hash family to describe this. So let's say this is a hash family. All random functions from u to n. Okay? What is the size of this hash family? How many functions are in this family? You're not technically allowed to say factorial every time I ask what is the size. If you want to use the word factorial, you have to say why it's factorial. It's actually not a factorial. So let's think about it this way. Every element of the hash family, you have to provide a rule that says, okay, so for the first, so let's write down all my u elements right here. For the first element, which of n buckets it has to go into? So maybe it goes into bucket 5. The next one has to go into bucket 7. The next one has to go into bucket 3. And I have to write this number down for each of these elements. So I have m choices for the first location. I have m choices for the second location. All the way up to m choices for the last location. Right? So this is basically m to the u is the size of this hash family. Okay, fine. How many bits do you need to write down one element of this hash family? Log of that, right? So what's log of that? So then we need, no, we don't need that. Right? Apart from the fact that this is terrible, what does this remind you of? There are u elements, and you need log m bits to write down its address. That's exactly what we had to do with the hash function. When we said, how do I recall the hash function? I didn't know which location every element mapped. So this is terrible. So we're kind of stuck, right? We had hash functions that did do what we wanted. We had a hash function that does evenly balance the load. But now it's too complicated. We can't write it down. And so the trick here, and the beauty of hashing, is that we actually can fix this problem. There is a way to use very, very few random bits, not this many, small number of random bits, to write down a function that will do exactly what we need, scramble the problem. And the function is something very simple. Let's not look at this. So the hash family. So the hash function, we call it HA. So let's fix a prime number P. Okay, and then the hash family, the hash function will look like this: HA of x is equal to and so the hash family so does the hash function make sense? So to unpack this thing, right, the mod m is obvious, right? You want the answer to be within 0 through n minus 1. So that's fine. The rest of it is the ax mod p. And a is a random number, sometimes called the sort in a hash function, that is being used to generate this. Now I'm going to prove to you that this does what it does, but I want to explain the intuition here. It's very simple, really. It's very clever. The intuition is that if you do ax mod p, and p is a prime number, so I don't know how much you're used to thinking what prime number feels, right? So the field the numbers mod p. You should think of it like a circle, right? So you go from 0 up to p minus 1, then you come back again, right? That's what mod p does for you. So it's a circle. Now think of what's happening when you do ax mod p. So I have some x, right? It's somewhere. You could think of even x mod p if you want. It's somewhere on this list. And now you do ax mod p where a is chosen randomly. What's going to happen? What's going to happen is I'm going to take x and move it to some random other location on the circle. And it's going to do this randomly for all of them. And it's going to be random because p is prime. We're using the fact that p is a prime number to make this work. Again, I'll prove all of this, but this is the intuition. So what we're saying is that, suppose I didn't have this first part. I didn't have the ax mod p. Then I'm saying every element goes to that mod n. So it's like in the low order log n bits. That's not much of a hash function, because everything with the same low order log n bits will hash the location. Now I'm saying, no, before I do that, scramble them all up. And then do find the low order log n bits. That scrambling step makes sure that two elements have a very small chance of having the same low order log n bits. Because I've chosen this randomly. And that's the intuition behind why this works. And I'm saying this because you will often find, and this is littered through the literature and algorithms, that if you want to generate randomness for free with a little bit of work, you use things like this. And why is it for free? It's because, what is the size of this hash family? How many hash functions in this family? There are p functions. How many bits do you need to describe the element of this family? Log p. So even if p is very large, log p is going to be very small. So we can make p quite large. In fact, we'll have to set p to be roughly something like much larger than u. But then log p will be log u. And that's okay, because you have to pay log u anyway to describe it. You need 64 bits to write down an IPv6 address. That's okay. So that's the idea. We've used very, very few random bits, exponentially fewer random bits. But because of the magic of prime numbers are kind of like this inexhaustible source of randomness in ways we don't fully understand. But because of that source of randomness that they give us, they sort of power boost a little bit of randomness to give us the same effect of having much more randomness. This is the intuition. I will prove these things, or at least somewhat prove them. Yes, take one question and we'll take it. Yeah, two questions. Okay, yes.
But A is a random number, right?
Yes,
So
A is randomly chosen from this range.
from A to B. So different hash functions in the same family, all of them have the same A or they have different?
No, each hash function is indexed by 1A.
Then I have to remember those.
Yeah, so you have to remember A, but how big is A? Log P.
Oh,
That's the thing, right?
before I do.
Exactly. I only need log P bits to generate my hash function. I've just written it down for you.
Okay.
I'm using the formula to help me generate the hash. There was a question back there. I thought there was. No. Okay, let's take a 2-minute break.
So, Suraj,
Yeah.
you said that the prime numbers generate
Yeah, it's a very mysterious statement. They do. That is also the case. You're right that a prime field gives the unique property, and we're going to use that property to show that basically there's only a unique solution for any mapping, and therefore, if two things collide, they're better. Or the probability of colliding is very small. So you're right about that in mathematical sense. But at a kind of a deeper level, the prime numbers. I don't know how to explain this. It's kind of an intuition that drives all around. If you want to get lots of randomness, use randomness. Yeah, and it's one of those things where once you see enough papers that use this idea, you realize it's really exact. You have a way of explaining this. Randomness is the source of randomness.
I'm having trouble hearing you.
So I said that in something the number is kind of a source of randomness because primes are. They're kind of unstructured but structured in some strange way.
Yeah, I don't know. It's hard.
It's hard to explain.
Yeah, as far as randomness.
But you know what?
Kind of.
Okay, yeah. So it's only kind of maybe.
Guys always associated them with uniqueness, but never randomness. So that's
No. So the thing is, that's the thing, right? The structure. If you look at some of the most fascinating questions about prime numbers are about like how are they laid out? Are they truly randomly distributed? Are they not? The thing with them is that kind of they're very non-random. Prime numbers are very specific constant, right? But in the way they get distributed along the number line, they look almost random. And that somehow leads to all kinds of things where, on the one hand, they're very well structured. I can use them. They're very deterministic in some sense. On the other hand, they behave like random, so you can produce random. Again, this is how we think about these things, these objects. Right? It's not precise. That's how a lot of mathematics works.
it's hard to find and generate large prime numbers.
Yes, it is. But that's because they're random. Because there's so hard to find. You can't really close. You don't know how to right.
They're always good. I'm not doing any course. I like I get thrills other ways. I have other high
Okay, let's continue. So one note, and again, this is from the feedback from people. This hash family, by the way, is not cryptographically secure. You may have heard of MD5, for example, and SHA-1, all these different cryptographically secure hash functions. We're not talking about that here. We're talking about simple hash functions. I mean, in other words, a cryptographically secure hash function would be one where given h of x, I could not figure out what x is. I'm not making any of those promises here. It is random, so it's kind of going to be hard for them, but we could crack. The other point I want to make is, remember, all you do in the algorithm is you have some hash family, you close your eyes, you pick a hash function. And that's it, you're done. Now you just build your whole data structure with that hash function you picked. So the only randomness is in the choice of A. Which A do you pick? That's all. And therefore the only thing you need to keep track of is that A that you pick. You write that down, that's your hash function. And you know that once you have A, this is how you define hash function. Yes?
So you only picked one hash function
Yes.
from the very beginning, you use that to hash all values?
Yep.
Okay.
That's it. It's a fixed, yeah. The
Okay.
only game, that's why it's so simple. The only game here is in which one you pick. Everything else goes back together, yeah.
How do you pick the P, the prime number? Is this just
How do you pick the prime number? Very good. How do you pick the prime number? All we require of P, first of all, it's not random. It can be fixed. All we require of P is that P is very big. And in fact, even that problem can be fixed. There is a discussion in the notes of how to deal with this if you're doing everything in word level stuff, so everything is a power of 2. There's a way to fix this so that P doesn't have to be very big either. Because that would be kind of inconvenient to have a P that's that big. So you need basically a 64-bit prime for your IPv6 example, or 65-bit or 128-bit prime. I mean, you can do these things with RSA and all, you need this kind of stuff, but it's hard to find. But that's all you need. For this proof to work, the proof that I have shown you to work, that's all you need. Okay? So I'm going to make a couple of claims, and some of these claims I believe I feel are kind of intuitive, so I'm not going to prove them, and the proof is in the notes, but I'll just state them. So the first claim I want to state is that this is the engine that makes this thing run. And I think this goes back to what you were saying in the break, Gary, that for, let's see if I get this right, yeah. So for any z less than p, there is a unique A such that so this is the unique inverse property, right? That if you have a prime field and you have a number z, there is a unique inverse A such that A is equal to B is equal to 1. Okay? Again, this is a very basic fact about prime fields. I'm not going to prove this, but this is why we need a prime number. This is not true in general. What you do have them, but they're not unique. You could have more than one thing that gives you.
If P is not defined.
If P is not. Okay, so it's unique. So the reason this is important is that what this basically is saying is this statement here is kind of the confirmation of my intuition here. What I was saying was that AX mod P is kind of like a random scrambling of X with respect to P. And that fact is what lets you say that. Because everything is a unique inverse. So every element maps to some unique other element, so you get a permutation. So essentially this process is generating a random permutation of the input. Okay, so that's the first fact. And the second fact you can show is that if you look at this hash function now, right? So if I look at what is the, let's select two numbers and see when they collide. So if we take two numbers x and y, they collide at h of a, x is equal to h of a, y. And since this is a linear thing, at least over the field, you can rewrite this as that, saying that h of a, with a bit of algebra, x minus y, is equal to 0. So this is not trivial, right? You have to make that, this only works because these functions are, in some sense, linear. I put in quotes, but it's all finite field, but they are linear. You can subtract. Basically, you get ax, you get ay, you subtract them. You can factor out a, and you get this. Okay? But what is ha of x minus y? It's basically a times x minus y mod p mod n. So you're asking for two elements that are not the same. For a number that's non-zero, when can you multiply by something like this and send it to 0? And again, because they're doing a random permutation, the probability of sending any particular number that's not 0 to 0 is 1 over n. So the probability that HA x minus y is equal to 0 when x is not equal to y is going to be 1 over n. Because everything goes to a random location. So that's what the randomness is equal to. Because it scatters it all randomly. This whole thing. So let me just put a line. So we now have a complete setup. We have a hash family, we have a way of computing a hash function, and we have a proof, or at least a sketch of a proof, with details of the nodes, that it has the desired property. That the probability of collision is what I said on the previous page. That the probability of hx equal to hy for x not equal to y is less than equal to 1 over n. We know that that property holds, the expected load is going to be equally close. So a chain of reasoning later, we have now come up with a plan, a quality that we want our hash family to satisfy, an actual hash family that satisfies it, and an effective way, an efficient way of computing this hash family. Any questions? And notice that all of this worked because we picked a random element. As we saw early on, because of the original principle, none of this will work if you have to be deterministic. You have to be randomized to make this all work. And that's why any hashing algorithm is going to use randomness. Now there's a long discussion that to be had, and again at a later time, not in this class unfortunately, about how random are your random bits. Are they really random? Are they pseudo-random? Are you listening to electrical noise and generating random? There's all kinds of questions about how random is your random actually. We won't get into that. But one way of thinking about what's going on here is that if you saw the ideal scheme that needed lots and lots of random bits, we've replaced it by a scheme that uses very few random bits and kind of boosts them up into enough bits to solve our hashing problem with the same guarantees as the true hash function. So you somehow have manufactured randomness out of nothing. And in fact, if you want to generate pseudo-random bits from a small seed that look like they're random, you do things like this. So this is an example not just of hashing, but how to manufacture random bits out of thin air. That kind of work for the problem. They're not truly random, but they're kind of random. And if you wonder what it means by saying they're not truly random, basically these random numbers are pairwise independent. The hash values you get, for any two things, the probability are the same as 1 over n squared, or whether they equals 1 over n. If you take 3 or more things, there are still other correlations among them. And that's how to randomize. Yeah.
Can you take two of them and make a quadratic number and get higher levels of?
Yes, you can.
Independence.
Right. So if you want to get higher levels of independence, like 3-wise independence or 4-wise independence, you would, instead of doing ax mod p mod n, you do a1x plus, you'd break up x into groups, and you'd have a1x1 plus a2x2 plus a3x3, and then doing that, you'll be able to get a bit more randomness. Yeah. So there are ways to generate higher orders of randomness using this basic framework. So this is a very good thing to remember as a tool for generating simple randomness.
The random numbers I generate from Ax mod p are not even pseudo, right? Random numbers.
Well, what is pseudo-random?
Pseudo is the hidden pattern, but here
No, pseudo-random is not a well-defined concept. Pseudo-random just means sort of random. So there they are sort of random. There's a formal way of defining pseudo-randomness. And you could say things like, for example, that any sufficiently stupid machine cannot tell them apart from truly random. And that's how we formally define pseudo-random. So you say a machine that runs in polynomial time cannot distinguish these bits from truly random bits. And that turns out to be sufficient for problems that are run in polynomial. So there's a way to systematically talk about levels of randomness, and this gets into all kinds of fascinating topics about how randomness relates to hardness and stuff like that. Again, completely out of scope, sadly. It's cool stuff. Any other questions? Yes.
So for fixed array of elements that we want to hash it to randomly, as long as the p value is larger, it is greater larger than p and a is some value between 0 and p.
Randomly chosen.
Yeah, we can get a decent hash shape table. So why do we still need to get a random number every time we hash an array of elements?
We don't. We choose A once, we fix the hash function it gives us, and we use that same function for all the elements.
I mean, for example, we have two sets of arrays.
Ah,
Two arrays.
yes.
We can definitely use the same value of A and P to hash these two arrays to hash them.
There, okay. Good. So the question, I think what you're asking is a good question. So suppose I wanted to make two arrays with two different sets. Can I use the same hash function for both these sets? If these sets don't talk to each other, you can. If these sets are going to be merged together into a single hash table, now it's going to be very small, the effect, but there's going to be an effect of this that you so wait, let me think for a second. The number of random bits. No, you're right. You're right. It does not matter. And here's why it doesn't matter. Take a thought experiment where instead of doing them separately with the same hash value, I had the two sets together to begin with. I would have done the same thing. The same random value. I mean, I could have chosen randomly in the same way. The choice of the randomness does not depend on the size of the two sets. It depends on the universe and the size of the table. The problem here is that in this case, the two hash functions, they're two different tables. So the size is now 2m. So now I have to ask you, how are you going to deal with that fact? If you put them into the same table, now my table size is 2m. Are you going to have a table size of m or 2m now? Because if you have a table size of m, now these things are going to collide. Right? And then you have to redo then you'll have extra collisions, and that would be accounted for. If your table size 2m, you can just concatenate them together, it won't matter. So it depends on what you're going to do with this table. If you're going to merge them or you're just going to stack them up on them. But since n is the controlling factor here, the size of the table, that's what will control whether this value is valid or not the number of elements. Now that's your question? Any other questions? Yes?
So how do you choose a reasonable n?
M is defined by your application, right? So you have so much storage. You want to store, I need, I have a budget of say, I don't know, a megabyte for my hash table. I'm putting it in cache somewhere. That controls it. That's the basic. So usually M is something that's kind of hardwired. You can't play with M too much. But having said that, let me get to the next point. Here's a little puzzle. Suppose in fact I had my n elements and I could choose my hash table M. Okay. We know that in expectation, because of that n over m property, if I choose a hash table of say size n over 2, then roughly speaking every element there'll be 2 elements in every table. Okay, so let me just write this down. I'm glad you asked that question because I was trying to figure out how to do the nice segue to my next point. So it was perfect. So let's say I have n elements. And let's say my hash table M is in fact of size n. Okay? So I have n buckets. According to my analysis, if I use a universal hash function, the expected load is going to be n over m. So I should see a flat. The question is, will I? If I randomly took n elements, so this is what it becomes what's called a balls and bins analysis. So the hashing problem now becomes the following problem. I have a collection of n bins. I have a collection of n balls. I take a ball and throw it into a bin. Take a ball and throw it into a bin. Do you think I'm going to get a flat spread like this?
We use the same function.
Sorry?
We use the function you have, you get it.
I will get it in expectation. On average, if I did this a gazillion times and average the load, it will be 1. But for any particular iteration, it will be completely not like 1.
No, it should be.
It should be?
Yeah, because AX mod P is equal to AX mod P.
All that means is that the probability of a collision is 1 over n.
No, AX mod P is unique, right? It always maps to 1 and 0
Sure.
to P. Now
Sure.
P is equal to n.
Yeah.
Then I have uniqueness out of it, right?
Yeah, but you're doing mod p, right? You're doing mod n. There's a such
Yeah, but
effect.
mod n, I would assume that P is greater than n, right?
P is greater than u.
P is greater than u. But u is 1 of n.
No, no, okay. Think of the thought experiment this way. I think this is good. So, you have your n elements into this gigantic universe. Okay? Now, think of a rope. The rope is my universe. Okay? That's the number of the universe. Think of my elements as little black marks I make at arbitrary locations along the rope. And then n of them. The process of doing AX mod P is the process of taking this rope and folding it in on itself. You're saying two black marks will never collide? I just said the probability of them colliding is small. I didn't say they will never collide. And if that's not enough, I'm going to fold this rope again to be of size n. So I'm going to take this rope and scrunch it up like crazy. By the way, have you heard this fact? Speaking of scrunching up rope, you take a piece of paper and you scrunch it up, there's one point in paper that will never move. Have you heard this? It's called the Banach's fixed point theorem. I just thought it was rope, paper, it's all the same thing. Anyway, so there will be things that collide if you do this rope. So there's no reason they won't collide. That doesn't happen very often. That's all I'm saying. In expectation, it doesn't happen. On average. But for any particular instance, all kinds of stuff will. And what we want to know is what is the all kinds of stuff. Okay? Alright. So, let's figure this out, shall we? Think of now the balls and bins. What is the probability that if I take n balls and n bins, that any particular bin, let's say the jth bin, gets more than k elements in it? What is the probability that happens? So what is the probability? So let's say I have a load. What is the probability that the load on J is more than K? So first I have to choose which K elements are going to show up there because it's random. So there are n choose K ways this can happen. And then the probability of them all showing up is 1 over n for each of them, right? Because it's random. So this is something like right? No. For each element. Yeah. Okay? And now I'll use some approximations as n choose k. And if you didn't know this, there was a way to simplify this, which is basically, yeah, so this can be written as oh, sorry, 1 over, let's make this, because n is more than n, because n is equal to, n is equal to n, right, which is, okay, so the probability that the load on the jth bin, if you throw n balls into n bins, is that's more than k is roughly 1 over k factorial. Which is a big number, which is why the load decays very quickly. For the load to be more than 5, it's 1 over 120. For the load to be more than 10, it gets much smaller. So the load isn't going to be very big. But there are n bins. Okay? So I want to look at the load on the max of them. So if any of them goes above k, I'm unhappy. So you can play some games here, and basically you can show that let's see, so let's do this here. That suppose you set k to be something like log n divided by log n. Okay? Again, you work this out to see why this happens. That basically the probability that the load is more than k is less than put a C here, is less than 1 over n equals C. So let's say this is 2, this will be 1 over n squared. And now if you say, okay, this is true for one bin, the probability that happens for some bin is n times this. So it's n times 1 over n to the C. So it's 1 over n to the C minus 1 plus 1 over n. So it's a very unlikely to happen. But that number k is log n. What you're saying is if you have n bin balls going into n bins with a very high probability, and I didn't show the other side of this, but you can show this a very high probability, the largest bin, the most heavily loaded bin, has load log n, not 1. It's much worse. So for any throw, your distribution is going to look like this. On average, it spreads out, but for any particular one, it gets really bad. There's, by the way, a very simple trick to get this down to log n, exponentially better. When you take a ball, don't throw it into a bin at random. Choose 2 bins and see which one is lighter and put it down. It's called the power of 2 choices, and it gets you down from log n to log n. Which if you used to think you were out, was a big win. Exponentially improve your load. Anyway. So if I have n balls and n bins, the load can be log n. It can be pretty bad. How many bins do I need to be sure that every ball goes into one, every bin has only one ball? You think if I do n log n, that should be enough. That's not going to work, right?
No, whatever you do, the probability, you can only talk about probability. You can never say.
Right, so let me rephrase. How many bins do I need to use so that when I throw the balls into the bins, the probability of any bin having more than one ball is very small, like 1 over n. Just the same way I had 1 over n here. That is the birthday paradox.
So can you go back, can you tell me how you got k is equal to C log n?
Oh, basically, you just plug it in. If you substitute C log n over log n and you put in the k factorial, you get 1 over n to the C.
Oh, okay.
Because k to the factorial is roughly like k to the k. And a simple trick is that if you want a number x to the x, such that x to the x is n, then x is roughly log n over log n. You have to work out the time. But this is a little shorthand that I know. So it turns out that if you want to have a certain number of bins so that no ball collides with a ball, if you have n balls, you need n squared bins. And again, the proof is in the notes. You should check it. It's actually a very simple proof. The reason why it's the birthday paradox is in the opposite side of this. That if you have less than n squared bins, right, then 2 things are going to collide. And so, when you say, okay, in a group of how many people do you need to have a collision in birthdays? Well, you think, okay, there are 365 birthdays. And so you need 365 people roughly. But you only need the square root of that. Because if you have that many square root of that many people, think of the birthdays as bins and the square root of that many people. If you have more than the square root of 365 people in a room, and you throw them into birthdays, 2 will collide. I normally do this demo in class. There was a time in this class when there used to be like 25 people in the class in the whole semester, and I would do this and I would hope that it would work, and it worked. It would be kind of silly to do it here. Because I could put money on this, it would actually work. But we could try it if you're interested. You want to try it? If the other 2 people in the same room in this room would have the same birthday? So normally what I do is I just go around and people just call out their birthday, assuming there are no security violations. But we're recording it, so we should do that.
Or we can ask
If you don't mind, you can do that, huh?
We can ask the other way around. Who has their birthday in January, and then it's binary search, right? To get faster match.
Yeah, but it might take longer because I don't know which day it's going to be.
Yeah, but there are only 3 people. Then they'll shout.
Well, okay, so wait a second. How many people are in the room? There are probably about 80, 90 people in the room. So that, and there are 12 months. So by Pigeonhole principle, there's at least 1 month with more than 8 people in it. That won't be enough.
Yeah.
More than 8 people. Well, we can try. Okay. How many people have birthdays in January? That's not going to work.
I think it's no, because you'll always put Pigeonhole.
Okay. Do you mind if I ask you to call out your birthday? Does anyone have an objection to this?
No.
If you have one person objection, I won't do it. Does anyone have an objection to this? Okay, so let's go on. Just call your birthday. Your birthday? And if you hear a birthday that's yours, just stop me, okay? June 12th.
September 22nd.
September 22nd.
August 6th.
August 6th. May 2nd. February? February 3rd,
September 16th.
September 16th,
December 5th.
December 5th,
May 16th.
May 16th. I'm getting nervous here. September 17th. What? Did I? No.
February 8th.
February 8th,
June 2nd.
June 2nd. Oh, wait. Oh. Huh?
June 2nd.
There you go. How many people are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's kind of cheating, but okay. But yeah. Within 12 people we got it. Okay, so there you go. But the birthday paradox says basically that. And you can think of it in terms of hashing. That if you want to hash n items so that you have no collisions, you need at least n squared bits. I think that was the answer to your question. Kind of.
It was, I mean, I guess there may be some number of collisions you'd be willing to have, maybe it's 5 collisions. So
Ah.
if you could,
If you want to have a constant number of collisions, it will be something very close to n squared for any constant. If you're willing to tolerate more than a constant, but say less than log n, then it starts dropping below n squared. So you think of it this way. I have n balls. N bins gives you log n collisions. N squared bins gives you 1 collision or less. If you want to triangulate between them, constant is basically the same as 1. So you're going to be something like n squared. If you're going to go super constant collisions, like say a log n collisions, then it starts going down further. Then you get back all the way down. So that's a good rule of thumb. If you want only 5 collisions, you're going to need close to say n squared over 5 or n squared over 25 or something like that. So again, you have to work over it, but it won't be much less than that. Okay. Thought I would cover more, but so I just want to say one more thing though. And there's a section of perfect hashing that you can read in the notes that will tell you about this. Namely, remember that I said that in this hashing scheme, even though the expected load is constant, for any particular instantiation of the hash function, you could have log n load. And that may not be a good thing. If these are say queues on a router, you want to be able to have a hard guarantee on the buffer size you need. An expected guarantee is no good for you. And the fact that the worst case could be as much as log n is also no good for you. And so a natural question is, can you guarantee that the worst case load is no more than constant? And it turns out you can. And the idea is basically that you build your first hash function, and that puts things in different buckets. And then you build a second hash function for those things. And then you show that the total space you need for all these hash functions, one for the master hash function, master table, one for the subsidiary tables, is still linear. But now the lookups are 1 here, and then 1 there. And the load is very small. So you only spend constant amount of time in the worst case. And that's called perfect hashing. It's a bit more involved. It's hard to do perfect hashing if you have your elements can change rapidly. That's a bigger problem that people look at. But that's something else you can do.
Can you prove it's constant?
Yeah. And the proof is in the notes. Okay. All right. Well, we'll have a good fall break, and I will see you back week after next. This is a desirable product. We would like this product for a really good idea. For the particular one that we're doing,